So let's try to rerun that again. Okay, so unsupported operand type S for tuple and integer. Oh, yeah, so I made a mistake here. Self.inChannels should just be equals in channels, not with this comma right there. So let's remove those prints. Is it just me that only debugs using print statements? Anyways, so let's run the model, and there's an error again. Torch.nn has no attribute leaky rel. Yeah, so rel. I think this should be capitalized. Rel. What the hell? Like that. Oh yeah, sorry. So this is 448. This should be 3. 448. 448. Yeah, like that. Yeah, so one thing here, it's also incorrect right there. It should be that, of course, when we've done the CNN block, the in channels to the next column layer we're going to create has to be modified. So the in channels now is going to be x of 1 instead of keeping equal in channels to 3. So you remember we did that update below here when we had the list. Then we did the in channels equals com2 of 1. But we need to also do it for the right here for the CNN block. Hopefully that is it. Please, please. Yes. So if we would take this 1470, we can reshape that. So, you know, if we would do, let's see, S7 by 7 by 30, that's 1470. All right, so that at least works as a sanity check. So, so that's our implementation of the YOLO model architecture. That I'm not sure how long that took. So here is the loss function for the YOLO algorithm, and there's a lot here. All right, so we have to step through it part by part and try to make sure that we understand this, and hopefully it will be even clearer when we actually get to implementing this. So first of all, let's just look at the sort of the overview of all of these losses. So all of these these parts of the loss function are going to be some squared error. So we're going to take the error squared and then take the sum. And you know, more specifically, if we look at this one up here, then we're going to have this is for the box coordinate for the midpoint. All right, so we're taking the midpoint x value, subtracting it with the predicted, taking that squared, plus the y value minus the y predicted, taking that squared. Okay, then this part right here is an identity function, and essentially we're only going to do that, first of all, if there's an object in the cell, and also if the bounding box j is responsible for outputting that bounding box. Okay, so I'll say that again. This is an identity function, this I right here. And the identity function means that it's going to be 1 or 0. And it's going to be 1 if there's a box in cell I, all right? And I is going to go from 0 to s squared. So I is going to go from 0 to s squared. So it's going to go through every cell in our image. And so it's going to be 1 if there's an object in cell I. But additionally, we need a requirement that bounding box j was responsible for outputting that bounding box. All right, so you might ask, well, how do we know which bounding box is responsible for outputting that bounding box? And if we just scroll down in the paper, let's see, it says here, it also penalizes bounding box coordinate error if that predictor is responsible for that ground truth box, i.e. it has the highest IOU of any predictor in that grid cell. So what this means is that we're going to look at a cell and we're going to see which of our bounding boxes, our predicted bounding boxes, which we have 2 of, has the highest IOU with the target bounding box. The one that has highest IOU, right, highest IOU, is going to be the one responsible, and that's the one we're going to send in right here. So we're only training the one here that's actually that was the best prediction. So because otherwise this is going to be 0. All right, so we do that, and we go through every cell and see if there is a object in the cell or not, and then we sum all of those together. Then we multiply with this lambda chord, and this is just going to be a constant because we want to prioritize this a little bit higher. So we're going to multiply all this loss by 5 because we really want to make sure that we can get the bounding boxes correctly. All right, so the second is right here is for the width. So we do the same thing pretty much. We have the identity function, we have the width minus the width prediction squared. The only difference here is that we have the square root. Let's say that we have a very large bounding box and we take those subtract and we take it squared. For very large bounding boxes, that squared is going to become very large. But for small bounding boxes, the loss is not going to be as large if you would have a larger bounding box. So what they do is that they take the square root to make sure that we prioritize smaller bounding boxes equally much as we do for large bounding boxes. And then we still have the identity right here, and we have the sum, and then we have lambda chord right there. All right, so those two on the top right there are for the coordinates, all right, for the box. All right, then for the next one right here, we have that C in this case stands for the probability that there's a box. So that's what we looked at previously. That was PC, the probability that there's a box in the cell. And so again, here we're only going to take the one that has the highest IOU, and that's the one that's going to be sort of responsible for predicting that there's an object in this one. So CI is going to be 1, and we're going to want to predict that the probability that there's an object is going to want to be close to 1. And so we go through for each cell and we go through every bounding box. Next is if there would be no object in a cell. Then we have this loss right here. So this, first of all, this loss above is if there is an object in the cell. The thing below here is if there was not an object in the cell. And then we're going to have that this identity no object, ij. So we're going to look if there's no object in cell I. And here is actually one thing that I found pretty difficult interpreting. So if there is no object, which is the one responsible for outputting that there's no object? In this case, they say that the one responsible is the one with the highest IOU, but in this case, they do not, or it's not clear to me which is responsible. Perhaps you can view it that it's the one with the lowest probability. That's the one responsible, or rather the highest probability. So you take the worst out of the two, and that's the one responsible. But in my opinion, it makes more sense to, if there's no object, then we should train both of the bounding boxes to make sure that both of them say there's no object here. So that's my interpretation of this, at least. And then we take the lambda no object, which is going to be 0.5, if I remember correctly. It's just going to be a constant to make so that we don't want to prioritize this as much. All right. So then for the last thing right here is for the classes, to make sure that we actually can say what object is it in this box, or in this cell rather. What we do is that for each cell, we look, is there an object here? So an identity if there's an object in cell I. Then we go through each class, all of the 20 different, and again we take the sum squared error. And so normally here you would do something like cross entropy loss, use negative log likelihood and do it like that. But here they actually want to use a regression based loss for everything, which simplifies a little bit, and it works apparently. So that's what they do in this one. All right, so let's try now to take this sort of overview, this understanding of the loss function, and try to implement it in PyTorch. All right, so we're gonna first do vim loss.py. So we're gonna open up that file, and we're gonna need import torch, import torch.nn as nn. And we're also gonna do from utils, import intersection over union. We haven't implemented, or we have implemented this, but I haven't put it in the utils file. So YOLO loss and then module. We're gonna do define init self. We're going to specify the split size S and B for the number of boxes. So we have 7 by 7 grid. The number of boxes we output for each cell is going to be 2, and then we have 20 classes. So first of all, we got to do super on YOLO loss, self dot init, and then we're going to specify our loss function. So self mean squared error. We're going to do mean squared error. We're also going to do reduction equals sum because they don't actually average it. So yeah, just trying to follow the paper right there. Then we're going to do self.s equals s, self.b equals b, self.c equals c. We're going to specify self.lambda no object is 0.5, self.lambda chord is going to be 5. So those are just the ones we need for the init. Then we're going to do define forward, and we're going to send in some predictions. We're going to send in some target. And remember that when we send it through the model, we need to make sure that they are reshaped so that they are s by 30. So we're going to do predictions equals predictions dot reshape. Let's just keep the number of examples. We don't want to reshape that, but we want to do self.s, and then self.c plus self.b times 5. So that's how we want to structure it. And then we're going to do, first of all, we're going to calculate the IOU for bounding for the first one. So we're going to do intersection over union predictions. And then we're going to take 21 to 25. Remember that we start at index 0, so 0 to 19, including 19 is going to be for class probabilities, 20 is going to be for the class score, and then 21 to 25 is going to be the 4 bounding box values for the first box. Then we're going to close that. We're going to take target. We're going to 25. Then we're going to do, let's see if I can copy this. We're going to do the same thing, but bounding box 2. And instead of taking now 21 to 25, remember this is not including the 25th one. So we're taking 21, 22, 23, 24. But now we need to change this to 26 and 30. And still, though, there's only one target. So we're still going to have target 21 to 25. Then we're going to do IOUs are just torch.catenate of IOU B1. And we're going to unsqueeze just to be able to concatenate them. IOU B2 unsqueeze 0. Then we're going to do dimension 0. So we're going to concatenate them along the dimension 0 that we just unsqueezed. All right, then we're going to take IOU maxes and the best box. We're going to take torch.max of IOUs along the dimension 0. So what we're doing here, torch.max is going to first return this thing right here, which we're not really going to use, but it returns the max values of the IOUs. But this thing right here is going to return the argmax of those, and that is something we want to use. So we're going to take which of the IOUs was the best one, meaning which one was responsible for that, which one was responsible for that cell or is responsible for that cell. Then we're going to do exists box is going to be target of 20. So that is going to be 0 or 1, depending on if there's an object in that cell. We're going to do unsqueeze 3. And yeah, so we could do 20 to 21 like this, but we want to keep the number of dimensions. When we take the 20th index, that last dimension disappears. So that's why we're doing unsqueeze here. We're gonna utilize this when we actually check for the loss functions. So this is, so you know, in the paper, this is the identity. So this is identity of object I. So and yeah, identity. Maybe we should just write I object I. So this is going to tell us, is there an object in cell I? All right, so now let's do for, first of all, let's do for, so let me just copy in what we're going to do. So first of all, so this is what we want to do. we want to first do for the box coordinates, and this means the midpoints and then the width and the height. Remember, we take the square root of the width and the height. Then we want to check what is the loss for the object loss, meaning if there is an object, we want to make sure that we output that, the probability of 1, there's an object here. If there's no object, we want to obviously say that there's no object. And then lastly, we want to make sure that it says which class the object belongs to. So those are the parts. So first of all, we want to take the box predictions. So the box predictions are going to be, first of all, if there exists a box, right, that we want to multiply. This is the identity part. Then we want to check which is the best box, and we want to times that with the predictions. So remember, this is going to be 1 if the second bounding box was the best, and the second bounding box is the one 26 to 30. But on the other hand, if the other one was best, so we're going to do 1 minus best box and times that with the predictions of 21 to 25. Because remember, this is going to be 0 if the first bounding box was correct. So best box is 0 or 1, depending on which one was best. And then we also times that with the existence of a box. So we only want to compute the loss if there is actually an object in that cell. All right, so after the box predictions, we're going to do the box targets. And that's going to be exist box times target of 21 to 25. Okay, so now we've taken for all 4, right? But what we want to do also is we want to take the square root of the ones that are for the width and the height. So we're going to do box predictions of all of them from 2 to 4. We're going to first do square root of the box predictions like that. But one thing here is that, if these box predictions are negative, which they are going to be in the beginning, just by initialization, then we have to take the absolute value, because otherwise we're going to get an error. So we have to do torch.square root, and we got to do torch.absolute value of the box predictions. But one additional thing is, what if there is 0, then the derivative of square root as you go to 0 is going to be negative infinity, or maybe infinity. Yeah, infinity. And so we're going to add, just for numerical stability, we're going to add 1e minus 6. And that's it. But we need to do one more thing, which is that when we take the absolute value, we need to make sure that the sign of the gradient is correct. So we're going to do torch.sign in the beginning here. So torch.sign of box predictions of all 2 to 4. We're going to take the sign of those, and we're going to multiply with the square root of the width and the height. Okay, so those are for the box predictions. And then the box targets, we're going to take 2 to 4. And these aren't going to be negative, because these are just the labels. So we can just do torch.square root of the box targets of 2 to 4. And I guess maybe one thing I should be a little bit clear on is why are we doing this ... And remember that all of them are going to be, I guess, n, comma, s, comma, s, comma, in this case, 25. So we want to make sure that we do this for all of these dimensions. So we have an example, but we also have s by s cells. And that's why I'm doing ... Yeah, so that was just one thing. All right, so box loss is then going to be the self mean squared error of torch.flatten of box predictions. And we're going to do n dimension equals -2. So what I'm thinking here is that we want to, why I did n dimension equals -2 is because we want to flatten everything in front. So, you can kind of view it that these NSS by 25, all of these are sort of separate examples in a way. So what we do is that we send in n times s by 25. Or rather, sorry, 4 for the bounding boxes. So this is not going to be 24. This is going to be 4, like that. And so this is going to become n times s by 4, because that's how a mean squared error expects the input shape to be. So that's what I believe, why I did that. And we're going to do torch.flatten of the box targets. And again, n dimension is going to be equal to -2. So we're going to close that. Then that's the mean squared error of the box loss. Yeah, so then we're going to do the object loss. So for the object loss, we're going to do, first of all, which was the prediction. And we're going to do that by taking the best box. That's the one with the highest IOU. We're going to take that time to predictions of 25 to 26. And so we're taking out the probability score. And why I'm doing this slicing right here is just to make sure that we keep the number of dimensions. So yeah, that's the only reason. And then we're going to do 1 minus best box, because if the best box is 0, then this is going to be the one that sort of takes over and is responsible. So then we're going to do predictions 20 to 21. And we're going to close that. And then we're going to do object loss is equal to self.mean squared error of torch.flatten of exists box times pred box. And why we're doing this is because we want to flatten to make sure that we have the same shape that mean squared error is going to take as input, which is that we have the number of examples here, or in this case n times s, comma 1. So we're gonna take that for all of these cells for each example. And I think we don't have to specify the start dimension here because it's going to do that by default. All right, so then we're going to do the same thing, torch.flatten of exists box times target. Like that. No, like that. So that's the object loss. And so, we're first checking which one of those two are responsible, which of the bounding box predictions are responsible or is responsible. And then we're checking if there actually exists a box. So this is for the identity part of the loss. So that's for if there is an object. In the case where there is no object, my interpretation here is that we're going to take the loss for both. Because if there's no object, I'm thinking it only makes sense that both of them should know that there's no object. So we're going to do no object loss equals self.mean squared error of torch.flatten of 1 minus exists box times the predictions of 20 to 21. And we're going to take start team equals 1. I'm not really sure if we need to do that. Oh, maybe, okay, so maybe here, the torch.flatten, I should probably check this up again, but I think torch.flatten here might flatten the entire thing. So, and that makes sense. We don't have to have this comma 1, so we can just have that. But here we want to specify start team equals 1. All right, so I think I'm starting to notice that there's a little bit of an inconsistency in how I've done this torch.flatten. In this case, it seems that we're flattening so that we have n, comma s, comma, in this case, just 1 for the no object loss, or no object for the box probability. This is going to be n, comma s times s, which I guess also works. But yeah, so I guess you could also modify this. I don't dare to do it though, because I want to make sure that the thing I've done that works is the one I'm implementing. But I'm thinking that you could also flatten this in some different ways. But yeah, so as long as we understand what's going on here, I think it's good. So then we're going to do torch.flatten. We're going to do 1 minus exists box. We're going to times that with the target of 20 to 21. And again, we're going to specify start team equals 1. And that's it for the first one, right? But then we got to do no object loss. And then let's do plus equals self.mean squared error of yeah, so let's actually just copy this because it's going to be very similar. So I'm going to take that and I'm going to remove that part. and then we got to do plus equals, and it's going to be 25 to 26, and then the target is still going to be 20 to 21. All right, so we're doing this now for both of them, which is how my interpretation is that we should do. All right, so for the class loss, we're just going to do class loss equals self.mean squared error of torch.flatten of exist box times predictions up to 20, right? So we're taking all of the 21st nodes, and the n dimension here is going to be -2. And so what we're doing here when we're taking n -2 is that we have n comma s comma s comma 20, and we're making this into n times s comma 20. So we're kind of viewing that each cell is a separate example, which I guess makes sense as well. And then we're going to do torch.flatten. We're going to do torch.flatten of exist box times target of up to 20, and n dimension is going to be -2 as well. And then we close that right there. And now for the actual loss, we have all those losses. So we're going to do loss equals self.lambda coordinate times box loss. So this is going to be first 2 rows of paper of I guess loss in paper, and then we're gonna add object loss here. Then we're gonna add self.lambda no object times no object loss, and then we're gonna add the class loss. So this would be the 3rd row, this would be the 4th row, and this would be the 5th row in the paper. All right, and then at the end, we're just gonna return loss. So what I'm gonna try to check here is I'm gonna put this in the complete directory and make sure that this works, because I haven't done test cases for this separately. All right, so let's just see. Here is the sort of complete folder. So I'm just gonna see Python train. Yeah, we got a conda activate deep learning. All right, best box is not defined. Best box, oh, okay, I used best underscore box. So let's run that again. Best box is not defined. What? We just did that one. Yeah, this should be best underscore box. So let's put this again and see if it works. Ah, my God, best box is not defined. Where did I put that? Line 29 here, but it should, right? Oh, yeah, so, of course, I'm not modifying that file. And so I need to modify that file. Let's see, so, okay, so now we can check. Hopefully it works now. Nope, line 53, best box, and then best box. Yeah, all right, all right, and it seems to work, nice. All right, so that was the complete sort of code that I ran it on, just to make sure that it works. And so now we have a correct loss function implementation, hopefully. All right, so now we have done the model.py and we've done the loss.py. But maybe before we do the training, let's actually make sure that we have the data set up. So before we actually implement the dataset class for loading the data, we need to make sure that we have the data, which involves quite a lot of steps, to be honest. So what I've done is that I've uploaded a zip file on Kaggle, that there's a link in the description. You can go there, you can download it. And this is actually going to be so this is 4 gigabytes, but I'm going to upload a smaller version if you don't want to download that entire thing, maybe few hundred megabytes or 100 megabytes or so, with just a couple examples so you can play around with the code. But if you want the entire data set, that's here, and then all you have to do is extract here, and then we should get a folder right here containing the data, and that's all that's everything we're gonna need. So let me just wait until this is finished. So if we open up that data folder, we're going to have